Hello, everyone. My name is Nafisa in Labonno, and I'm an undergraduate freshman studying physics at UT Arlington. Today, I'll be presenting to you my research on neutrinos. So let's look at the process of hypothetical nuclear decay, where two neutrinos in a nucleus simultaneously decay into two protons, emitting two electrons, which are beta particles, without any accompanying antineutrinos. So this process is known as the neutrinoless double beta decay, which is also shortened as nu-DOBE. This nu-DOBE is effectively used to monitor effective field theories and investigate its properties. So the ways in which we do it is try and look at an experiment called the neutrino experiment with a xenon 136 time projection chamber, which is our next experiment. So the reason why next generation exploration of nu-DOBE is important is because it allows us to identify, because of its ability to reconstruct particle topology with precision, the next experiment can probe the subtle deviations in the topology and therefore probe potential alternate models to the standard light neutrino exchange paradigm. What that means is the current understanding of the standard model will then be enhanced, and then we will enter a different paradigm of physics, or rather a new physics world, which is the beyond standard model, or BSM for short. So what is this nu-DOBE, and why are we interested in this process to begin with, right? So nu-DOBE is a very rare phenomena. In fact, it is a hypothetical phenomena which has been speculated for a long time to understand whether or not neutrinos are their own antiparticles. And why are we interested in that topic to begin with? Because we want to understand whether or not because if, for instance, neutrinos are proved to be their own antiparticles, we will then understand a very important phenomenon, which is the lepton number violation, or LNV for short. So this research talks about how a very simplistic yet very powerful tool called a Python, a very powerful tool which is based upon a Python program called nu-DOBE for short, which is derived from the name of the beta decay process itself. Nu-DOBE is then used to advance our understanding of computational techniques that can be calculated that can be used to calculate the beta decay rates. So currently what we are lagging behind in is our understanding of computational techniques and our efficacy in measuring, let's suppose, LNV operators, or speculate higher dimensions up until dimension 9, for instance. So this is where nu-DOBE comes in to play, and this is where the experimentation is reached to its fruition, right? So we look at how this nu-DOBE incorporates. By the way, but nu-DOBE we're talking about is the Python tool. This incorporates renormalization group running and matches the low energy EFD, or effective field theory, which is therefore able to account for various sets of nuclear matrix elements and hadronic low energy constants. What this does is it allows us to see beta particles in the detector, which can be a reflection of which can be seen here on my right. This is our next 100 experimentation picture, which shows one of the iterations of the next generation exploration of neutrino-less double beta decay. All right, so what is this next experiment all about? This is a study that allows us to investigate the topography of electron tracks, and allows us to understand how we can try and understand the different momenta and build tracks off of it, right? So nu-DOBE allows us to implement different models such as all of these, and is therefore a very powerful tool that can be used to change various mathematical constants such as NMEs, such as Wilson coefficients. And why is that helpful? It is helpful because it is essentially the higher energy physics that is driving our effective field theory, right? And this physics is encapsulated in the terms of effective field theory, and is called the Wilson coefficient. And we are able to, via using nu-DOBE, we're able to alter these coefficients and predict different observables, which is extremely, extremely important for our understanding of future next work. And with that in mind, thank you very much for listening to my speech. And yeah, thank you.